you. First, I want to thanks to Takimasa, actually. I'm not an ENK person, so I don't know most of you, actually. But of course, I know now more of you because I workshop. But I work with Shu-Hua, who is a LETK person. So today, I want to talk about using the airborne GPS RO data, radio occultation data, and the impact on the Hurricane Karl. That's happened in 2010. There's a field campaign called PREDICT, also the GRIP, actually. So there's a 3-field campaign going on at the same time. And then, so I'm looking at one of the storm. I want to acknowledge all the people working together on this one. This is really mainly done by my student. Also has the same last name, Chen. But then there's a people, this is a study from the instrument collecting data and do a retrieval. And we are the downstream people using the data for assimilation. And even this is a 2010, actually, we didn't really get the data in a good quality until almost end of 2015, actually. So my student was unable to graduate because we couldn't give her the good data. Anyway, so let's see, just give you a little bit of brief view about this occultation data in case you're not familiar. So I'm talking about the spaceborne force because theory eventually are very similar. So you have a low Earth orbiting satellite. So when the GPS signal is sending out, when it's passing the atmosphere during the setting or the rising of the LEO, then you can collect in all the GPS. You can collect in the signal passing the atmosphere, and because of the density, the refractivity, the ray is going to refract and bend, right? And that's give you the information of the atmosphere. So you can see just when it's passing. So this is one of the settings. So you got a bunch of the rays. And then there's a most close to the Earth. That's called a tangent point or PRG point. And that's usually most of the retrieval data available there. So what's good about the GPS data? Compared to other satellite data, I'm more like a satellite person. So compared to other satellite data, the GPS data basically is not impacted by the weather, and that's very good. For the microwave channel, over the heavy rainfall area, you couldn't get a retrieve data. And then for the IR, near IR data, you got all this cloud issue. But this is a very good data, which doesn't have this cloud or heavy rainfall issue. And it also has a very high vertical resolution, okay? So how people use the data? The observable data actually is a phase data. So you got a phase delay, and there's assumption. Like the impact parameter, you have a sort of symmetric assumption. That one is not too strong, but you got a bending angle. After bending angle, you have very strong assumption, which you have to assume that atmosphere is a local spherical symmetry. So you use this a Bayer inversion. You study from the bending angle, get the refractivity. So you can think about the Earth as like an onion. It's a symmetric onion. And that's how you get it from the bending angle, and then you got a refractivity, which is at the PRG point, the tangent point. That's the data you're supposed to get. So the refractivity can be written as a function of pressure, temperature, and water vapor. So you expect you're simulating the data, you're going to get all this information into the model. So just a little bit overview of this cosmic 2006. So you have this the 6th LEO in the atmosphere, and then you collecting all the data because this is a high inclination orbiting. So you can see a lot of data actually is over the pole region, right? That's what you see. And over the tropics, that's pretty empty. This is 1-day data. It's a lot. But if I'm looking on a specific time window, 3 hours, 6 hours, it's very sparse. Especially if I'm looking at the tropics, that's where all these are hurricanes, and it's even less. And then you can see this is from 2006. You have a lot of data. 1 day about 3,000. Until now, it's really cut it to almost like 1,000 or less. And of course, there's a cosmic 2 coming. I think they're supposed to went up last year, but it didn't happen. Hopefully this year is going to happen. 6 of them is going to have a low inclination angle orbit. So you will get a lot of data over the tropics. So that's a very good part. You have a lot of data here to compensate this more like a polar orbiting one to the high latitude. So the whole project here was actually happened much earlier, right? There's no cosmic 2 at that time. And of course, don't have a cosmic 2 either. But this airborne data is try to just put an instrument on the airplane, and so you can fly to the area of interest, so you can get more data. Later, I'm going to show you one of the cases we are studying, and you can see how sparse the cosmic data, and that's why this airborne data can give you additional information. So you can see this is the airplane. So basically the airplane received the signal still the same, the rising and the setting of the GPS. You got the data collected by the airplane, and then this is the PG point. The red color is the PG point. So the motivation, I pretty much mentioned already. So basically the motivation is because the spaceborne GPS is very sparse, and then the data is very good. So now how can we get more data, right? And that's where this airplane, which is a Jennifer's group, then try to get this instrument and then get on the airplane to collect the data. And again, this is on the PREDICT under the NSF project. And so the goal here is to try to assimilate the GPS data, evaluate the impact, and use the different operators. Just give you a quick view of this, how you can see this, how big this one is. So it's actually pretty big. So Jennifer, they are trying to do a mini version of the GPS receiver on the airplane. Hopefully, they will get funding and try to get a smaller size and a more accurate. Actually, I think this instrument on the airplane is not accurate as a spaceborne. And that's why the signal noise ratio is a little bit low, and that's why it's very difficult to get the data at the very beginning. Now they are getting better, but still has some problem, okay? All right, just a little bit overview again, review again this spaceborne and the airborne data. So this is a spaceborne at the left side. So you can see the GPS both are the same, but on the right, the left side you have this LEO, and then this is the airplane. So airplane basically inside the atmosphere, that's how you get the data, where the LEO is outside the space. So this is basically this equation is written more like a symmetric. So this bending angle is a PG point, which is a tangent point here. So you do the integral from here to the top of atmosphere, so it's 2 times. So basically, it's the bending angle starting from this point to this point. While the airplane is only from this point to here, it's the same, but here to the airplane, this is shorter. So if you want to do this retrieval, remember the retrieval assumes it's a symmetric, right? So this wouldn't work. So you need to do a little bit work here on the airplane. So, and also there's one thing I want to point out is the tangent point, the horizontal drifting, the tangent point, the airplane is almost 2-3 times of the spaceborne GPS data. So the spaceborne GPS is drifting about 150 kilometers. The airborne is about 300 or more kilometers. So it's horizontally drifting a lot. Okay, that's a PG point information. So for this airborne data, how are you going to do it? So this is an airplane, assume this is a schematic diagram, the airplane is here. So you have either the same GPS or different GPS. You got this a positive elevation angle, it's above the airplane. You can see the height is above airplane. While another one, the ray is passing below the airplane, okay? So this is a negative elevation angle. So what are you trying to do? Again, there's an assumption here. These two has the same impact. So eventually, you can have this negative elevation angle subtract this positive elevation angle. So eventually, you will get the partial bending angle over this area. Now it's a symmetric in a way. Of course, it's not symmetric, but the path looks like a symmetric. So you can do a retrieval now, just like you do for the airborne, for the spaceborne data. So that's how this whole thing works. But also, you have to keep in mind the airplane shouldn't be too low. Otherwise, these two cancel out seems a little bit too big, right? I mean, assume they are the same. That's what the retrieval does anyway, but you will try to keep the airplane a little bit high enough, so this assumption will be not too bad. All right, so Jennifer's group already compared the retrieved data, the refractivity with EC interim data. So then figure out the error is about 2%, that's what we need to use in data assimilation. And also you can also find below the 2 km, actually the data actually has a bias. So meaning when we assimilate data, the data below the 2 km is all kicked out. We are not going to use the data, which is not good. Okay, so when we assimilate refractivity, the 2% is what we use as error information. All right, so I'm going to show you the case study here. So we have this Hurricane Karl 2010. So this is the track. It's passing the Yucatan Peninsula and come to here. So the genesis, I believe, it happened on the September 14. And then here you got a category 3, okay? So actually I was on the airplane, I was on the grid, I was on NASA DC-8. So I went up to look at the storm and then the car was very difficult to predict. Everything looks so good. Every day just check, everything's checked, but genesis never happened, actually. There was a really long history, and then there's a day I have to decide I should go back to Davis or I just stay longer. I said, oh, maybe, there's no hope, so I left, and then the storm developed. so bad. So at least I went up to look at the storm one time, but I didn't get through this category 3. That's all people dream to go up to look at the hurricane eyes. I missed it. All right, so this has a very rapid intensification. So you can see the pressure drop to the 9, below the 960 millibar. Okay, so this is a very interesting time period. People are all interested in this one. This is when this passing over the land. That's why it's weakened. And then you can see this is a wind reached to like about 55 meters per second. So for the Karl case, the predict, actually the NSF project, this one have a 6th flight. GRIP is more interested in the later on, but the predict is more interested in the genesis. So they are kind of, across the different time. But you can see the different color is a different flight. And as I mentioned earlier, the Karl is very difficult to predict. So somehow the people even started earlier, it's very difficult to get a genesis happen. So we try to get only this particular date at September 13, one particular flight. And so this flight is about 1 day before the Karl genesis. That's what we pick up at the time. And this is the data of that day. So all the green color indicate the PG point, the tangent point of each ray. So each one is like each occultation. Okay, so this is an airplane floating around and flying around, and then all the blue stars are drop sounds. And the red dot is a cosmic. So you can see the cosmic just like hanging around, but never really hit the storm close enough. And we tried to cosmic and really didn't have an impact. So one thing I want to point out good about the airborne GPS is you can see this, the drop sound, usually you drop at the airplane, right? So it's kind of vertically going down, but you can see this airborne GPS, it's a side looking actually. So it's very compensating the data you have as a drop sound. So basically it's look the side of the drop of the airplane is, so you provide another dimension of the data for people like us want to do the data assimilation, right? So you can see there's a lot of interesting data here. I want to give you another view of how this data look like. So this blue one is a PG point. So this is another one actually. They flew over the California, outside California, Edmonton River. It's very hot this year because we have a lot of rain in California. Okay, so but this is not taken this year. This was like 2015. So the fly is flying, say this direction. So you can see the first point, the first one, that PG point is always have one side attached to the airplane. So the starting from the airplane, that means it's a setting. So the satellite is setting, right? Starting from airplane height and keep go deeper and deeper. So basically this blue is a PG point, and the pink line, each pink line is one ray, the occultation ray, okay? So that's how you can see this kind of dimension of the picture. And this pink line usually can be about 700 kilometers along the path, okay? And then again, the PG point is about 300 kilometers for airplane. For the cosmic, it's about 150 only. And this one is, again, another view how you see this one. This is airplane, just fly, and this is a GPS. So it's collecting the data. So you can see it's collecting the data through the atmosphere. And that's the PG point. That's the tangent point. So you can see horizontal drifting, okay? So back to here. Now we know a little bit about the data. How are we going to use the data? So you have a bending angle, or you can have a refractivity. And then how are you going to use the data? And of course, we know there's a very strong assumption it's a local spherical symmetry, right? So if you use the refractivity, you are getting the data which has a bigger error. And keep in mind, the good data, why you are going to use a low quality of data and try to make the error bigger, right? So let's see how we're going to try to look all use the data. So first it's a refractivity versus the axis phase. So that's a refractivity. You already know. You do this retrieval, assume the symmetry, and you got the data at the PG point, the tangent point, and that's what this operator look like. Pretty straightforward. Okay, that's the operator. The second one is that you're going to do the axis phase. So basically the B prime is the axis phase. You basically integrate the refractivity along the path and then give you the axis phase. However, if you are doing the original B prime, it's actually quite difficult to do polarization because you don't know the ray, because the ray wouldn't know until it encountered an atmosphere and then do the bend, right? So people try to do is just use A prime to approximate. So once you know the PG point, you know the azimuth angle, you pretty much can know the rate exactly, and then you can do a polarization. Bill Gore then did already this one. I think the speed is amazing. Our code is still serial code, okay? But they have a parallel code. It's like instantaneous and got a result, but we had to run a long time to get a result. But I think that's the original motivation. People try to use a straight line, the tangent line, to do the approximation and then claim the result is not that bad. Of course, then use a much closer resolution. But anyway, this is a non-local operator we use. So basically, you do the integration of the refractivity along the path. So we have two different way of using the data. One is a refractivity, and one is axis phase. The second one is the drifting versus non-drifting tangent point. Some people try to not, a little bit, I don't know if it's lazy or not, but try to just treat the data as a column data instead of the drifting data. So as I mentioned, for the cosmic, the drifting is about 150 km. For the airborne, it's 300 or even high, larger distance. So you don't want to do that. The most important is if you go to the high resolution, like our resolution, I'm going to show you the second domain is a 9 kilometer. So it's a drifting about 30-degree point. So you want to do the drifting or not, you have to, ask, kind of try to see how you're going to do take advantage of the data, right? So that's why we are going to do this drifting, non-drifting. This is one of very long drifting PG point. I'm not quite sure how this happened, but it's really, really long. Okay, but I specifically point this one is because this one has a sensitivity test of this sounding. All right. So if you look at this one, I just give you a view. Make this three-dimensional project onto a two-dimensional. That's what this looks like. So just lump sum everything collapse to a two-dimensional plane. So this is the PG point. So I suppose this is the airplane here, and that's how this vertical look like. Okay, and this each ray. So you can see this array has according drifting, the rays look like this way. Well, if non-drifting, if you do the column, then that's what this is going to look like. First, they are all passing different ray. The ray passing atmosphere is different actually. All right, now I'm going to show you some numerical experiment and then some result. So we try to set up the 3 domain, and this is just one of the time the data available. You can see all of this occultation data here. So this is 3 domains. The resolution is 27, 9, and the 3 km, and this is all the physics scheme we use. And this is a pretty old version, 3.2, because again, as I mentioned, it was a long time ago. The whole thing just didn't work because the data quality was so bad. And then we calculate the background error occurrences, use 60 pairs of the warp forecast, and use the NMC method to do it. So this is the experiment. So basically, we started from 00Z, September 13, and we only ran 12 hours. The very end, that's where the airborne GPS data all come in. It's like about 3-hour window, it's all coming in. And then after that, we do 4.5 hours of the forecast. So the experiment, the control run, just have an original GTS data plus the drop sum. And then the most important is about the last 2 later, okay? So the N means refractivity, and then the E means axis phase. So we have original whatever in the control run plus the airborne GPS data, but it's a refractivity, either non-drifting, which is the column data, or drifting, which is the subscript, the D here. So you can see this will be axis phase, a column data, non-drifting of the tangent point, and this is a drifting of the tangent point. Okay. So before we go to D, I'd like to see first the result. So this is a sea level pressure, the minimal sea level pressure, and the time. So the black line is observation. So you can see they are all nicely following. That's very nice. Pretty much have a genesis happen. But you can see the rapid intensification. So only these 2 reddish, red color, warm color, is kind of have a rapid intensification. The others do not have. So the control run, which is a purple color, you can see it's come back. And then the other 2, as long as it's a column data, non-drifting, then almost the same as a control run. With the drifting, then you can see they are different, the rapid intensification. So first, you've got a message. The drifting is very important, which is not a surprise. I mean, drifting 300 kilometers horizontally, I don't see why you don't use the information, especially this is high resolution simulation, the forecast. Okay. So now we look at the analysis. So this one is a control analysis increment for the total precipitated water, means vertical is a column integrated water vapor. All right, so this is all just whatever other data contributed. And then the most important is what do we gain from the GPS. So basically, this minus control is only coming from the GPS. So you can see this is a 3D bar. Okay, that's why everything is like a circle, not like the flow-dependent ENK looks very nice. But this is all just like a circle. What I want to point out here is that you can see this particular sounding. So this is only negative. So basically, it's like just try to take out moisture in the atmosphere. That's what this all DA does here. But the yellow means you try to put the moisture back into the atmosphere. But there's one here, this is 13. This is all blue color here, means all the negative. While this one, actually, you can see along the ray, there's a positive close to the higher up of the ray. So you can see taking the advantage of this drifting, it actually gives you a very different result. So this is all coming from the refractivity, and now this is coming from the axis phase. So one thing you can see right away is axis phase, the increment is bigger. Okay, it's bigger, that's for sure. And of course, there's some subtle difference between the two, but later I'm going to point out this one specific sounding. But there's a few things here. There's a positive soundings here. I mean, like a increment here. These are pretty important one actually. So if we took out those moisture, then the storm will behave like a control run. So those moisture are pretty important. These are positive, are very important actually. And then you can also see this analysis at the 3 kilometer. So again, everyone is subtracted the control. Basically, it's contribution coming from the GPS. The wind is a full field. Okay, so you can see the shading. The shading itself is the pressure difference. Oh, so quick. I should skip a lot now. Okay, so you have some vorticity here. So this high pressure anomaly, of course, give you this, the anticyclonic circulation wind anomaly as well. So you get this a pair of the vorticity, but this vorticity might have some impact to the storm as well. I want to point out a few things here. One is, we don't have this exact analysis time, but we compare 6-hour forecast. You can see this positive moisture, which are actually very important to the storm development. So assimilating this GPS data, was able to recover some moisture field here, but you can see the model was unable to do something because there's not much data there anyway. So it's too dry over this area. And the track, okay, this is again, the red color is the one that has a drifting. That's not bad. There are some better than the others. And again, this is the one I showed you earlier. With the drifting, it's better. Now the question will be why? I'm going to show you this animation. This is a vertical integral water vapor. And the left side is I'm only looking at the axis phase because the refractivity actually, the increment is too small. But then you can see here it's much drier here compared to this one, right? So you have to pay attention to this dry air because this dry air actually intrude inside this Karl. I even wonder the model couldn't do well because this dry air just couldn't handle very well. So you can see it's start sucking into the center of the storm. We just do one time, okay? So you can see here the dry air kind of coming. So with this column non-drifting, you can see this dry air coming into a storm, and this one has a less, right? I'll quickly go through here. There's one thing very important: the upper level vorticity and the low level vorticity lined up. Actually, this alignment of the vorticity is very important in this vertical, in this genesis intensification. Actually, so I'm going to skip everything here. Also, this is another thing. It's very important. It's the down shear side of the storm, the convection. It's very important when it's doing the intensification. But you can see a lot of evaporation. The green color is adiabatic cooling. So you have a lot of evaporation over the down shear side of the convective cloud, which is going to suppress this intensification, actually. All right, so this is the key here. What happened to this particular storm? I already showed you the animation, right? You can see that dry air suck into the storm. And really, if you look at this earlier time, the 21Z15 compared to this one, actually there's one particular spot close to the storm actually has a diabatic cooling actually because of the evaporation. And it's actually pretty deep. So what do we try to do? You can also see this dry air. This is blue color is like dry air here. It's kind of go very close to the storm, where the drifting one actually is a little bit more away from the storm. And then what we did is we tried to do some backward trajectory, starting from here and go back like a 2.5 days. The air is coming from where exactly that sounding is actually. So it's coming from that sounding. So that sounding, the result is very sensitive to that particular sounding. So either you handle it well or you don't handle it well, or you just don't do it. If you don't do it, still didn't get it, right? Because the control run is the one, okay? So I just want to point out one more time here. This is give you the innovation of this axis phase with the column and the drifting. So again, one is this way and one is here. Looks very similar. Of course, they are not exactly the same because the paths are different, okay? But what's the increment? So you can see the increment with the drifting. This is where close to the storm side, okay? And this is where the Q-bound. So you can see with this drifting, actually, it's not that dry as this guy here. This is very dry, actually. And also here it's more moist. When it's close to the storm, it's more moist, okay? So I just want to point out how important, with the information there and how you're going to use the data. That's really important. I know the methodology is important, but the data itself is also very important, okay? So these are the two. Once we take out this sounding, then both develop with the axis phase. We take out the sounding for the refractivity, then both do not intensify like original. They will behave like a control if you do the refractivity. But if you do the axis phase, if you take out the sounding, both develop actually. So again, how you use the data, it becomes very, very important. All right, so I'm going to put everything here. What I want to point out is here is the last one, how this ENK method is going to better take the advantage of the information given by this non-local observation, which usually have a smaller error compared to the retrieved data. Okay, so this is something I think is really important. I mean, I think the variational people probably do not have much concern on this one because, I mean, there's an A joint there and there's a better way to put back in, but I don't know, there's an ENK people here, and it would be nice to know how you're going to handle this non-local observation. Just give you what we are doing now. So we are trying to do the same case, use LET cave. We have the code inside the Shu-Ha's code actually, but just play around and try to play this non-local information, see if we can see something interesting. The second one is we try to do some RC study for this Colorado, the flood case, 2013, and this is where the rainfall. So what we try to do is we put every commercial flight a GPS receiver. And then we can simulate the track, we can simulate all the occultation information, there's a simulator. And then we try to evaluate what's the impact. If it's good, and if it's not expensive in the future, then why not put the instrument on the airplane? They are flying every day. Of course, you will not do the airplane high enough, that's good, not too low. As I mentioned earlier, there's an assumption there. Okay, that's all. Thank you.